Just because it was all watchable last time, let's just start with a recap of a few terms. So I'm just going to ask some definitions-y questions. Give me an informal sense of what they mean. What's a function? Yeah.
No repeating x values. Is that right?
Yeah, that's relevant for what we're going to do. So tell me what you mean by that.
Like, for the same graph, a function would have any of the x values that would pick up this.
Yeah. So I'm going to translate that, instead of saying x and y, I'm going to say a single input, because that's kind of what you meant by x, right? Yeah, so maybe I'll add a few words. This is still somewhat informal. It's just some rule that takes an input, probably a number, and returns some output. A single input can't go to multiple outputs, but that's the only rule. A function is just some rule that does that. If you do have a function, what's the domain of that function? Yeah. Yeah, so one way of saying it, it's like all x values. And that's a very graphical definition. We'll talk about that soon. Maybe I'll give this as a self-contained one that doesn't mention x's, because the independent variable isn't always called x. Everything that you can actually plug into to a function. That's its domain. What about the range of a function? Yeah, so let's write down both of those. So we'll be talking about graphs today. If you have the graph of a function, the range is covered by all of the y values that are actually accomplished. And if you like, that's because the y values are the outputs. All of the output values that actually get hit by the function. Folks feeling pretty good? All right. So maybe one last one. This one is going to be a computational question. So I'll ask you to walk this out. Well, f of x equal to x squared plus x plus 1. Tell me, what is f of x plus 1? And this definitely isn't like an exam or anything. Feel free to talk with those around you. Once you have an answer, go ahead and compare with those around you. See if it agrees. Cool. So I haven't walked this out in advance or anything. What are people getting? Yeah.
X squared plus 3x plus 2.
Agreement or disagreement?
Plus 3.
The answer with the plus 3? The answer with the plus 2? Other answer? Should I talk through it? Yeah, let's do it. So, what does something like f of x plus 1 mean? Well, f and then a thing in parentheses just means take the input variable and replace it with a thing in the parentheses. And especially when it's something slightly complicated, I'll color code this a little bit. I won't worry about exactly what the thing I'm plugging in is. I'll just put a little placeholder there. F of box. So I know what f of x is. It's you take that thing, x, you square it, then you add it to itself. Then you add 1. So f of box is box squared. And in order to make sure I square all of it, I'll put some parentheses there. Plus box plus 1. And what do I want in the box? Well, it looks like I want x plus 1 in the box. So if you want to evaluate a function inside of a function, just replace all the inputs with whatever that is. And now expand, right? So I guess step 1 is, well, I guess let's try to do 2 things at once. Let's combine those 2 things together. Do those 2 parentheses actually matter? No. Addition is associative, so if you only see a bunch of things added and subtracted from each other, you can erase the parentheses. That bit is just x plus 2, I think. And here I see x plus 1 squared. Sorry, what does it mean to square? It means you should multiply the thing by itself. How many people, if they saw this, would tend to want to write that down? Okay, good, because that is incorrect, right? And even if you know it's wrong, that's an easy mistake to make. Squaring doesn't distribute nicely over addition, because what does squaring mean? It means you multiply the thing by itself. And then how do you actually multiply out 2 binomials? Because you use the acronym FOIL, or you use the distributive law. They're both the same. X squared outside plus x plus the inside plus x plus 1 plus x plus 2, just carry that bit down. 1x squared, I see 3x's plus 3. Neato. Folks feel okay? That example was useful, I hope? Good. So whenever, say in one of the web work problems, you see a function plugged into a function, go through a process like that. You might do it in fewer steps, that's fine. That's the general mindset to have. All right. Oh, and as a reminder, right, I am recording this right now. So this will get posted if you just want a recap of that example. So let's get into what I want to do today, graphs of functions. And you've already said a bunch of things in the language of graphs of functions. Right? domain is like all of the x values, but really you meant all the x values that are on the graph of the function. The range is all of the y values on the graph of the function. But let's build up just what does that even mean? If I give you a function, what is the graph of that function? Yeah, and they're like paired up, right? Each input is telling you what its output is. So maybe I'll put it in the language of xy coordinates. So it's all points, x comma y points, with y equals f of x. So x is allowed to go through all of its possible values, and for each of those x values, there's a corresponding y value, namely f of x. So let's just put that into practice. Let's just test that. So right here, I claim this is the graph of y equals the square root of x. Let's first answer like an easy yes-no question just by looking at that graph. Is 4, 2 on that graph? Should it be? So it is on the graph because it's like this point. Should it be is like, it requires more than just a yes-no. Why is 4, 2 on that graph? Yeah, right? Square root of 4 is 2. When you plug in x equals 4, the resulting output is 2. Should it be? Yes, since the square root of 4 is 2. So this x value corresponds to that y value. Looking at that graph, are there any points with x equals -1? No, why not?
Can't get the square root of negatives.
Yeah, if there were an xy value with x equals -1, y would have to be the square root of -1. If there were, then you would have to have y equals the square root of -1, which is something that's not real. So this is actually one of the things, at some point in the past I said, well, there's another tool called Wolfram Alpha, which is, my objection to it is it does too much. It'll try to graph the square root function, and it'll graph it in a way that makes you think that maybe you can plug in a negative. Because it'll try to do some stuff to graph the complex part also. Which is fine, but if like you don't look carefully at what it's doing, it might lie to you. Yeah. We do. So we won't do much graphing with them. And the reason for that, if you like, is you picture like imaginary numbers as like already being on a plane. So you would have like 2 dimensions worth of inputs and 2 dimensions worth of outputs. So you need like 4 dimensions to really graph a complex function. And there are ways around that you can like have those 2 other dimensions be designated by colors. So you can see like really cool heat maps out of complex graphs, but we won't do that in this class. In fact, that's a fun thing to do in Wolfram Alpha, graph some complex functions. Cool. All right. So let's just close with one more thing about graphs of functions in terms of x, y values. If you see some function and you only know its graph, you can evaluate that function using the graph. To get f of x, look for the y value over that x value. And you know what? Maybe I'll go slightly off script. Let's use that graph. There's the graph of y equals the square root of x. Using that graph, what does the square root of 2 seem to be approximately? Sure. It's 1.5-ish. How did you get that? Yeah, so you looked over x equals 2. You said, well, I see a y value that's there. at this particular scale, it's hard to do much better than just 1.5. It's pretty close. It's like 1.44-ish. So you can at least approximate any given output value over an input value by looking at a graph. So let's see that in practice for this. So let's suppose that here is the graph of a function. How many people are already upset that I say that's the graph of a function? Okay, cool. Well, let's try to read this off. So there's the graph of a function. Using the rule that I just stated, if that's y equals f of x, then tell me, what is f of 1? Yeah, say it louder.
1 and negative 1.
It's both 1 and negative 1. You look over this x value. I see two different y values. They seem to be about 1 and negative 1. F of 1 seems to be both 1 and negative 1 by using that rule. Are functions allowed to do that? No, this is like there are some weird laws made up like multi-valued functions when you want to allow that sort of stuff. But if you just say function no, a single input can only go to a single output. So is that actually the graph of a function? Nope. And when you said like each x value only goes to one y value, that's what you meant. The x values are the inputs. A single x value can only have one y value over it. And we summarize that in a thing called the vertical line test. The vertical line test says the following. If you have some graph in the xy plane, this is still the graph, it's just not the graph of a function. It is the graph of a function if over each x value lies at most one y value. And let's just see if that holds up. This was the graph of the square root function. If we start fixing some single x values, this graph is going to get messy. Well, if I take like this x value, how many y values are over that x value? I think there are none, right? The one that's way over here. Yeah, so 0, at most 1. And notice, like, those are the numbers that you can't even plug in. So it's not surprising there are none. If you take, like, a positive, or maybe 0 also, x value, do you see at most one y value over that x value? Yeah, that's all the vertical line test says. So let's just use that to make some quick tests. Are these graphs of functions? Okay, for each one of them, let's just answer yes or no, maybe by a show of hands. This first one. Yes? No. Cool, why not? Yeah. Yeah. At some of those x values, I see lots of different y values. Notice at some of them, it looks like, over this one, it looked like there's only one. But even one place where it fails is a failure of being a function. All right, this next one, is it or is it not? Folks for yes? Folks for no? Cool, yeah, absolutely. All right, you start drawing some vertical lines. Yeah, it looks like each one of those hits the graph at most once. There's only one y value over those x values. That last example? Folks for yes? Folks for no? Cool, yeah, it's a function. The next couple examples are going to correspond to these two things graphed to the right. So let's start with just this question. Are those graphs of functions? Yeah, awesome. That means we should be able to use these functions to make some evaluations. Let's do that. And I think I'll jump, well, maybe I'll just give you a second. Fill in those blanks, f of 0, f of negative 1, f of 1, f of negative 2, and the same thing for g. this particular class is very quiet, which is like fine. One of the things I'd like to see is, like, especially with example stuff, is just kind of quick compare with those around you, because that even like lets me know that people are about done with this example and not just wandering deeper into the note packet. Cool. So let's come together. F of 0, and be approximate if you have to. 1. Folks agree? Nice. Anyone want discussion on that particular one? All right, cool. F of negative 1. 0, right? Because the point x equals negative 1 corresponds to y equals 0. It's a solid dot, so that point is actually on the graph. F of 1. Yeah. 1.4-ish. Right. And maybe you're saying 1.4-ish because that looks vaguely square root of 2 looking. Yeah, realistically, looking at that graph, you probably couldn't really get that many decimal places. It's somewhere between 1 and 2, though. F of negative 2. Does not exist. Tell me why. Yeah, like there's an x value of negative 2. These instructions to understand the graph of a function says look for a y value over that. And there isn't one. So f of negative 2 does not exist. Let's do the same thing for g. G of 0. Also non-existent. G of negative 1. Yeah. Agree or disagree? Disagree. Other disagrees? Cool. Why not?
It's an open dot, which means that's not that value.
Yeah. The open circle means that that point is excluded from the graph. There isn't actually a y value over x equals negative 1. And this is a sneaky way for me to also remind you of some notation. Whenever you see an open circle on any picture, that means that that point is specifically being excluded. All right, on the other hand, G of 1. This one is negative 1 because there's a solid dot. Solid dot means that that point is specifically included. Whenever you see a graph and it looks like there's an endpoint and it's neither shaded nor open dotted, really there's just a failure of communication. It's not clear looking at that graph whether that point should be included or excluded. You should decorate the endpoint somehow. G of negative 2. 1.75-ish. Folks feeling good? So notice, we failed to be able to evaluate these functions at some points. The domain is like all of the places where you can actually evaluate the function. So the fact that we failed to evaluate the function means that we know some things are not in the domain. We know that, for example, negative 2 is not in the domain of f. Looking at this graph, could you just tell me what the domain of f is? Yeah.
Negative 1 to 3.
Negative 1 to 3. Are you including or excluding?
Including.
Nice. And so how do you get that? Well, you want to know what inputs can you actually plug into this thing. And we have a set of instructions. If you plug in inputs bigger than 3, it looks like there are no y values over those x values. So all of those new bits of that pink line aren't actually included. You can't evaluate the function. Once you hit 3, yeah, you're in. Everything between 3 and -1, you're in. At -1, we evaluated it there. You can find the domain by looking at a graph. Same thing for G. What's the domain of G? Yeah.
-3 to -1 with a bracket around the and then 1 with the bracket to 3 with the
Nice. Folks agree? Yeah.
Would you do the union sign in between?
Yeah, so if this were like a written homework and you want to do that, or like the ampersand sign, I'd know what you mean. If you happen to be using the computer software WebWalk, it'll want a union symbol between. So what the union symbol means is you want anything that's in either one of those two sets. And that is what you need in this case. You just need to be in one of those two to be in the domain. Yeah.
G -2, isn't it 0.75 instead of 1.7?
Yep. Did you say 0.75? Let's take a look. So you look over x equals -2.
Yeah.
Okay, well, happy?
Yeah.
All right, yeah. And you will find that a lot of time I fail to think critically when someone tells me something with enough confidence. And if it happens to be wrong, go ahead and correct me. Also, whenever I should do something wrong, correct me. It'll happen a lot. So let's talk about this, just put that into words. You can read off the domain of a function from the graph by just seeing what x values you see on the graph. Oh, yeah, absolutely. And maybe I'll make this little bar go away. And that's exactly the process we just followed. Whenever you see a graph of a function, you can always just read off the domain. Maybe the endpoints will be approximate, maybe you can't quite tell exactly where they are on the graph, but you can figure out where they're pretty close. So the next thing I want to talk about is let's use a graph to solve an equation. So here's again the graph of a function. For what input or inputs is this function equal to 2? Well, let's think about what this means. I want like the output of the function to be equal to 2. So whenever you see f of x equals 2, really you're thinking the output is equal to 2. The output, that's the y value on the graph. I want to figure out where on this graph y is equal to 2. And let's start with this. Does it look like there is an x value where y is equal to 2? Yeah, it's like this point-ish. And I'm incapable of really drawing a straight line, so maybe this isn't totally trustworthy, but what about looks like that x value? Say it louder.
3.
3, yeah. And you know, whenever you're reading off something from a graph, you're never going to have 100% precision. Let's answer this question though. This is just a yes-no question. Is 3 an output that this function actually hits? Yeah. So it's in the range. So x equals 2, y equals 2 is actually in the range. Nice. Is there, what if I asked you to solve f of x equals -1? for what x values is f of x equals negative 1? Yeah. No, there are no x values with f of x equals negative 1. How'd you get that? Yeah, so you checked out negative 1 for the y value, and then are there any x values where this function hits that? So, indeed, there are no solutions to that equation. Is negative 1 in the range of this function? So there are no solutions to f of x equals negative 1. So negative 1 is not in the range. If I ever give you something that looks like f of x equals c, c is some number, maybe it's 7, maybe it's 12, don't know. Can you always read off the solution to that equation by looking at a graph like this? Yeah. Draw the line y equals c, record all x values where the graph hits that line. And maybe there are other ways to say that, like you want to record all the x values which correspond to a y value of c. So let's maybe say this now. So we can compute the domain from a graph. This is certainly hinting that we can compute the range from a graph, right? So give me some odds. Well, maybe we'll even just ask. If there's the graph of a function, what's the range of that function? Yeah, let's check that. So what this says is leave out anything that's negative, but then include 0 in the range and include anything positive. Does it look like those y values below 0 are in the range? Good. That checks out with that answer. Is 0 itself in the range? Is there an input which gives you 0? And then if you keep going up, will this graph cross each and every one of those horizontal lines? Looks like. Maybe it's hard to tell for sure. Maybe it like levels off and flattens, but it looks like it probably doesn't. Yeah, looks like the range is 0 to infinity. And whenever you should interpret a graph as like continuing forever in that direction, I'll decorate it with a little arrow. Or I'll try to. Sometimes I'll fail to do that. So let's think about how you did that. So what was the mindset? How did you find that range by thinking about the graph?
Swap the thought process for the domain.
Oh, cool, yeah. So instead of reading off like the x values, you read off the y values?
Yeah.
Yeah, cool, because y values are outputs. So the range of a function, given its graph, is all y values, which are on the graph. And if it weren't for the fact that we're on a previous page, I'd flip back to that previous page and like copy down exactly those same ones, but replace x with y, which I think I've done okay-ish at that. Same in spirit, anyway. So let's see that in practice. Here are some graphs. I even told you what the functions are. Tell me, what are their domains and what are their ranges by looking at these pictures? I think I'll even, let's include some vertical lines. Think about their domain and range, and then we will come together. All right, let's do it. So that first function, if you like, that is the square root of x squared minus 1 minus 1. But you don't really need to know that to compute the domain or range from a graph, right? That's extra information for context. What's the domain of that function? Yeah.
Parentheses, negative infinity, negative 1, bracket, union, bracket, 1, infinity, parentheses.
Cool. People agree? How many people instead said something like all real numbers except those between -1 and 1? Would that also have been correct? Sure, yeah. That's also correct where you were. What about its range? Yeah.
Bracket, -1, comma, infinity, parentheses.
Cool. Nice. Next one. Is anything not in the domain of the next example? No. Looks like all numbers are in the domain, and there are a few ways to write that. All numbers are in the domain of this function. Maybe if you really, really like interval notation, it's -infinity to infinity. Mathematicians sometimes like to summarize things with symbols. The symbol I'll use for all real numbers will be blackboard bold R, which just literally reads as all real numbers. What about its range?
Bracket,
-2 to 2. And the -2s are actually, the 2 and -2 are actually included because there are some x values that achieve those y values. Semicircle. Y equals 2 times the square root of 1 minus x over 2 squared. And in order to account for those open circles, I'll even advertise that I am forbidding y from being equal to 0. So what's the domain? Yeah.
Parentheses, -2, parentheses.
Cool. Folks agree? All right, the open circles say that those should be excluded. What about the range?
Parentheses 0 to close bracket.
0 to 2. And maybe just in order to indicate one thing, let's suppose that one was replaced with a solid dot, which would mean that's erased. If that were a solid dot, how would these answers change? Close bracket on positive 2. Does the range change? Yeah. The 0 would be included. Notice, it looks like 0 is different from the other output values in that it's only accomplished once. But the range doesn't care how many times a single output is achieved, as long as it's at least once. All right, this last one, inverse tangent or arctangent of x. What's its domain? All real numbers, and however you want to say that is fine. If this were WebWalk, it might say, well, you have to enter it in an interval notation, but you know how to, -infinity to infinity. What's its range? Cool. And notice, just from a graph, you're correct in excluding those, but you can't really tell that from the graph. Maybe the curve would actually hit that dashed line and stay there. It doesn't, but you can't really tell that from the graph. Neato. Folks feel good? All right. One last thing then. So we've talked about functions and domains and stuff, and we've done like nothing that could be called really applied today. Let's do at least one made-up example. It's not a made-up example. I mean, this is really what would happen. So let's suppose you take a wheel of radius 2. So the radius is 2. There's the central. You put a little dot up here at the top of the wheel, and then you set it to spinning at some speed. So its linear speed is 1 foot per minute. That just means that the speed that the actual dot is traveling is 1 foot per minute at any moment. If you do that, then, well, you expect the, like, dot's y value is going to go down and then back up and then back down and then back up. Well, in a world where there is no friction, I guess, so it's never going to slow down. It's just going to keep on going. If you do that, then the height of the wheel, the height of that red dot, it's supposed to be a red dot. I know this doesn't matter. The height of the red dot as a function of time is given by a graph like that. So let's just read off some things from that. What's the height of the red dot when the model begins? Four feet, at least according to this graph. So I guess this graph is, the wheel is already sitting at a height, with its bottom at a height of 0. So the middle of the wheel is at height 2, the top is at height 4. And you know what? If this is actually supposed to be applied, there are probably units the height's in feet. The height at time equals 0 is 4 feet. What's the height of this wheel after 8 minutes? Well, we have a graph, right? Let's just read it off from the graph. So this means you want to know, yeah. Oh, you can't see the graph. You want to know what the height is at t equals 8. Well, t is like the input value. So the x value, this is why I didn't want to say x so much, because sometimes the input isn't x. Let's see what happens at time equals 8 minutes. 1, 2, 3, 4, 5 minutes, 6, 7, 8 minutes. There's t equals 8. What's the height at that time? About. Say louder. About 0.7-ish? That seems about right. It looks a little bit bigger than a half, so let's call it 0.7. At what times is the height 3 feet? Yeah, say it louder. 2 minutes and 10.3-ish minutes. How'd you get those? Yeah. So you said, well, I want the height to be 3 feet. So you drew that line at 3 feet. And you saw one at 2 minutes-ish. I'm going to make that approximate too. And then another one at 10 minutes plus a little bit. Is there another time? Nice. So you can read off lots of things from a graph. And I have just about 1 minute left, maybe a little less. So let's answer this one last question. How long is it going to be before that dot comes back up to its starting height? About 12.5 minutes. And I don't know, how many people feel good about their trigonometry? Give me something more precise than that. this is definitely not something you should just know. That 12.5 is 4 times pi. And that's not something you should, I mean, maybe that like sounds right to you. If not, don't worry about it right now. Cool. So we'll start with next time is something that will look an awful lot like the open-ended homework assigned for today. It'll have to do with piecewise functions. So take a look at that. If it doesn't seem familiar at all, don't worry too much. We'll think about it on Wednesday. But, take a look at it. If it seems like something you can do, then the example that we'll do in class will seem much more familiar. Which one would be easier for you? Both of them. As long as it's a readable PDF, then I don't care if you write how much.
It's hard to get like some of
Oh, sure. Yeah, whatever you can do that is readable. If you're like typing it out, then most equation editors have okay. Most word processors have okay equation editors. They're not perfect, but they're fine. If you want to write it out using a pen and take a picture, that's fine. Which one are you going to do?
Okay. Probably that.
Yeah, you got some days to decide.
Thank you.
Yeah.
It's a picture of what we're talking about.
Yeah, I think you're describing doing something kind of silly. So you're already typing up like a Word document?
Yeah. Because it wasn't handy or anything.
Cool. So that's like a really ugly way to do that.
For like if it's an hour.
No. I just instead of taking a screenshot, export as PDF. Yeah. Yeah. Was that also answer what your question is?
So we export this.
Yeah. So are you like typing it up already?
It's like I usually write it down.
Oh, that's fine.
Should I type this?
If you want to. Is your handwriting legible?
Yeah.
Yeah, that's fine.
Okay.
Yeah, so digitize it somehow. There are like scanners all over. There are scanning apps on phones that we can use.
Do you have an iPhone?
Yeah.
You know how to do it with that. Through the notes app. So instead of scanning the PDF right now, all you do is open up the notes app. And you just open up your file scan. So you open up your file and you scan that. Literally all it is just hold it over it.
What file format is that?
I think you can change it, but it's uploads to PDF.
Oh, goes right to PDF? Okay.
Once you transfer it to computer, then it's
Okay, yeah. Okay.
yeah, it's really simple.
Yeah, so I know that like some of those default to like file formats that NVIS doesn't know what to do with, like HEICs.
Yeah, I don't know.
Okay, perfect.
I saw it, I recognized it, I was like, we're good to go.
Yeah. Nice.
Where is it?
So, with like 5 minutes, I should probably stop recording at some point.